Hi everybody. Hope everybody's having a good day today so far. Today we are going to talk about compact sets and some implications of compact sets. In particular, we are going to talk about closed sets again. We talked about them just briefly earlier on in the course. We're going to then talk about the Bolzano-Weierstrass property, which of course is related to the Bolzano-Weierstrass theorem that we proved in a recent lecture. We're going to talk about compact sets and talk again about the Weierstrass theorem, and we'll actually give a proof of the Weierstrass theorem today. So let's get started. So let's start off with a characterization theorem for closed sets. So you'll recall that we defined a closed set to be the complement of an open set, and that was it. So if we could identify the open sets, we could identify their complements, and they would be closed sets. Here we have an alternative definition, a characterization theorem, which means that in effect it's an alternative definition of a closed set. And this definition here enables us to identify sets that are closed or not closed without reference to open sets. We can just reference the set itself and its properties. And so the definition here says that a set's closed if every sequence in the set, every sequence of points in the set that converges, that if every sequence in S, you can see how you can easily get confused because the word converges is appearing twice in a row here. Every sequence in S that converges to a point in S. That is, if the sequence converges, it converges to some point. And for closed sets, it's got to be the case that when that sequence converges to some point, that point is in the set. And of course, that's what the implication down here says. It says i.e., so this implication here is an alternative formal way of saying this. And it says, if it's the case that every term of a sequence is in the set S, and the sequence converges to a point x bar, then that x bar has to be in S as well. So, of course, we can take, it's always a good idea with any theorem to not only be able to see how to prove it, and by the way, we're not going to prove this theorem here. I believe it's approved in the lecture notes. If not, I'll probably give it as an exercise because it's quite straightforward and simple. Oh, and let's just note that it does say if and only if. So it is a characterization theorem because it's if and only if statement. When we have a theorem, it's important to be able to prove it, but you know, it is maybe equally important to have counterexamples to the various assumptions in the theorem showing that if an assumption in the theorem doesn't hold, if it's not present, then the theorem doesn't work. That is, the conclusion of the theorem doesn't necessarily hold. So let's do that here. This says if every sequence in S that converges to a point in S, well, let's take the set. Let's take the set S equals the open interval in Rn. In R, let's make that in R. So let's just take that n off of there. The open interval in R, and of course that's not closed, not a closed set. And we can see that it's not a closed set by taking a sequence of points in S. For example, we could take the sequence in which xn is 1 over n. That sequence converges to 0, so 0 would be a limit. So in the definition over here, x bar would be 0, the limit of this sequence, and 0 is not in the set. And of course, I could also take the sequence in which each term is 1 minus 1 over n, it converges to 1, and 1's not in the set. So this set is very much not a closed set. Not a surprise, we already knew that, but it's a simple counterexample showing that if our sequence has a limit, if any sequence in the set has a limit that's not in the set, it's not a closed set. So let's next just remind ourselves of the Bolzano-Weierstrass theorem that we already saw and we already proved. We proved it in R, in the reals, and I suggested that you could go to the lecture notes or you could go to Simon and Bloom to see a very nice proof that extends the theorem from R to any finite dimensional Euclidean space, Rn. And so the Bolzano-Weierstrass theorem says that every bounded sequence in Rn has a convergent subsequence. Now I've just put that on for reference. Next, notice that we have a definition of something called the Bolzano-Weierstrass property of a set. So this definition says that a set has this Bolzano-Weierstrass property. We do a kind of shorthand of just saying BW as a kind of abbreviation for the Bolzano-Weierstrass property. If every sequence in the set has a subsequence that converges to a point in S. I've put the in S kind of in gold here to emphasize it. So if we have, let's say, a bounded set. Suppose S is a bounded set. Well, that bounded set, any sequence in the bounded set is a bounded sequence. And so the Bolzano-Weierstrass theorem would say that in that bounded set, since every sequence is a bounded sequence, it would say that in that set, every sequence has a convergent subsequence. But the Bolzano-Weierstrass property of a set requires that when we have that convergent subsequence, the convergent subsequence has to converge to a point in S. So let's come back over here and let's take a similar example. Now let's take S to be the set from -1 up to 1 in R. And let's let the sequence that we're looking at be the sequence that is -1 to the n times 1 minus 1 over n. That's one of the sequences in those 5 examples that we had when we were talking about sequences and bounded sequences. So this sequence, every term in the sequence lies in S. So if we were looking at the Bolzano-Weierstrass property, this would be a sequence that qualifies in the sense that it is a sequence in S. It's a bounded sequence, of course, because S is bounded. So any sequence in this bounded set is going to be a bounded sequence. And this sequence, because it's bounded sequence in the real numbers, the Bolzano-Weierstrass theorem says that that sequence will have a convergent subsequence. And we've already seen that. So this is just review here. Of course, it has a subsequence that converges to 1. That would be the subsequence consisting of the even terms, so that -1 to the n is 1 always. And it has a subsequence is more than just 1. It has subsequences that converge to -1, and that would be a subsequence consisting of odd numbered terms, so that this is always -1. -1 to the n is odd, -1. So that would be a sequence that converges to -1. So it's certainly the case that because this set's bounded, any sequence we take in the set will be bounded, and the Bolzano-Weierstrass theorem will apply, so it will have a convergent subsequence. But this sequence does not have any convergent subsequence that converges to a point in S. The convergent subsequences are only subsequences that converge to 1 and subsequences that converge to -1. There aren't any subsequences that converge to anything else. So there are no subsequences of this that converge to a point in S. So this set S doesn't have the Bolzano-Weierstrass property, even though every sequence of points in S does converge. Sorry, every sequence in S does have a subsequence that converges, but it doesn't have subsequences that converge to a point in S. So that's the critical point here. And sets that have this Bolzano-Weierstrass property are sets that we call compact. Now, you may have, in fact, I'm sure you have, used the idea that compact sets are closed and bounded. That is, compact is kind of a name for the closed and bounded sets. Well, what we're saying here isn't quite the same as that. We're saying that the name compact for a set refers to sets that have the Bolzano-Weierstrass property. And so they may or may not be closed and bounded, but notice the next theorem that we have, which says that in Rn, a set is compact if and only if it's closed and bounded. So indeed, in the reals, or in Euclidean space, Rn, or maybe RL I should use so I don't confuse it with the n's in the sequences. So in Euclidean space, RL, Rn, indeed it is the case that the compact sets are the ones that are closed and bounded. So if you in the past have only been working with the real numbers, or you've only been working in Rn in Euclidean space to define compact sets as the sets that are closed and bounded, it's perfectly okay because it's going to work out just fine. Those sets, in fact, will be, evidently, the sets that have the Bolzano-Weierstrass property. Those will be sets where every sequence has a convergent subsequence that converges to a point in the set. But in vector spaces, norm vector spaces, metric spaces, in spaces that aren't Rn, in particular, in infinite dimensional spaces. So that would be, for example, spaces consisting of sequences, R infinity. That set, together with a natural norm on, let's in fact not take all of R infinity, let's take the bounded sequences in R infinity. That set, together with a natural norm, the sup norm, is infinite dimensional, and in that space, the sets that are closed and bounded don't necessarily have the Bolzano-Weierstrass property. So in infinite dimensional spaces, unlike in Rn, RL, in infinite dimensional spaces, sets can be closed and bounded, but not be compact, could not have this very useful, powerful Bolzano-Weierstrass property. And I'll come back, I think, and mention that again after we've done a few things with compact sets here as we move forward. So here we have a theorem, and now we're going to provide a proof of that theorem, and then we'll take that theorem and we'll get 2 or 3 more theorems that are consequences of this theorem here. So I'm going to take this off the screen to give us some room to prove this theorem about compact sets being closed and bounded. Okay, so now we're going to give a proof, or let's see if we can prove this theorem about compact sets being the closed and bounded sets. So let's put our proof over here. And let's start by proving that compact sets are closed and bounded. Then when we finish that, we'll do the converse, that the closed and bounded sets are actually compact. So we'll say, to start with, assume that S, whoops, that's supposed to say is, I jumped ahead to do the C before I did the S. assume that S is compact, and that means, of course, that it has the Bolzano-Weierstrass property. So what I want to do is I want to show that S is both closed and bounded. So let's say first, suppose S is not bounded. And we'll hopefully be able to get a contradiction, and that will establish that S has to be bounded. So if S is not bounded, then for each natural number, let xn be an element of S such that the norm, and we're in Rn, so I'm going to have to use the norm, not the absolute value, such that the norm of xn is greater than n. Right? So this forms a sequence, since I have an xn for each natural number. So I have a sequence, and the sequence is obviously not bounded. It's not bounded, and moreover, it's clear it's not just unbounded, because unbounded sequences could have convergent subsequences. But this sequence, more to the point than being not bounded, it has no convergent subsequence. Subsequences always have terms that get larger and larger and larger. And so it has no convergent subsequence. If it has no convergent subsequence, then it certainly doesn't have any subsequence that converges to a point in the set. So contradicting the Bolzano-Weierstrass property, which we assumed when we assumed that S was compact. So therefore, it has to be the case that S is actually bounded. Okay, so we've established that the set is bounded. Now let's say suppose that the set is not closed. So suppose S is not closed. Well, if it's not closed, go back up to our definition of our alternative characterization definition of a closed set. And so if the set's not closed, then it has to be the case that there is a sequence of points in the set S that converges to a point that's not in S. Right? So this says it's closed if every sequence that's in S that converges to point in S. So we must have, if S is not closed, a sequence in S that converges, but it doesn't converge to a point in S. It converges to some point outside S. So then there has to be a sequence in S and an X bar not in S such that the sequence converges to X bar. You have a sequence in S, converges to a point not in S, set's not closed. Well, if we have a sequence that converges to X bar, then every subsequence, this is I don't know if it's a theorem we've proved in the lecture, but certainly it's one that's in the lecture notes, and I think we may have done this in the lecture. If we have a sequence that converges converges to, say, x bar, then every subsequence of that sequence has to converge to x bar as well. So this says that every subsequence of this sequence in S converges to a point not in S, so there aren't any subsequences that converge to a point in S. All right, so let's just put that in here. Then every subsequence, I'll just denote it that way, every subsequence converges to x bar, again, contradicting the Bolzano-Weierstrass property, which is what we assumed. So therefore, we have a contradiction from assuming that S is not closed. So therefore, it has to be the case that S is closed. So we have proved that any compact subset of Rn will be closed and bounded. Now let's see if we can go the other way. I don't know if I can squeeze that in here on the screen, but let's give it a try. So let's say, assume now that S is closed and bounded. I'm actually going to switch to a different marker here because this one, the writing is getting a little fat, so let's hope this is a little better. We'll see. So we assume the set's closed and bounded, and what we have to do to establish that the set's compact is we have to take an arbitrary sequence of points in S and show that it has a subsequence that converges to a point in S. We have to show that S has the Bolzano-Weierstrass property. So let's say, this isn't a lot better, but a little better maybe. Let this be a sequence in S. Then, since S is bounded, this sequence is bounded. And since the sequence is bounded, and it's a bounded sequence in a set in Rn, the Bolzano-Weierstrass theorem tells me this bounded sequence has a convergent subsequence. So let's put that here. S, and therefore N are bounded. Therefore, Xn has a convergent subsequence. Subsequence. Let's even write it out here. It's xnk, let's say. And xnk converges, so it converges to some point x bar. To some x bar. And since the set S is closed, this subsequence, which of course is a sequence in its own right, converges to x bar. This is entirely in S because the original sequence is in S, so the subsequence is a sequence in S that converges to x bar. So we'll say S is closed. We assume that. Therefore, x bar has to be in S. So what we've done is we took an arbitrary sequence in S and we showed that it has some subsequence that converges to a point in S. That is, we've shown that S has the Bolzano-Weierstrass property. We've shown that S is compact. So that completes the proof of the theorem. And so now we know, and we can see the details as to why it is the case that in Rn, the compact sets are the closed and bounded sets. So that's, of course, the reason that what you've done before this course, if you've used compact sets in Rn, you've just used as a definition that the compact sets are the closed and bounded sets. So now I think we want to take this proof off, and we want to see what more we can get out of the fact that the compact sets are closed and bounded. So we'll take this off, and then we'll be right back.